Hello folks, this is the first of the sequence of videos that I'm preparing for using the explicit dynamics in the 3D Experience platform, which is essentially the Abacus's explicit formulation being used in 3D Experience. Now, I have done quite a few FEA videos for 3D Experience slash Abacus CAE, but they were all using the implicit dynamics and therefore, or statics. I've never done one in the explicit dynamics, and I'm beginning to make these videos now. Remember, these videos are for people who want to transition to 3D Experience and maybe they have experience with Abacus CAE, but the problem is that although it's the same program buried in there, but the interface is completely different. And one should not expect that if you're an expert in Abacus CAE, you can do right away, very quickly, 3D Experience's version of that. Okay. The purpose of these videos is to go through certain problems that have been done by other YouTubers using the Abacus CAE and then repeat or replicate those steps in the 3D experience format and interface. Okay, this particular problem that I'm doing is coming from the source that you see down here, and it's and this particular by the way, this particular illustration is also coming from the same source. It's a square aluminum tube which is being crushed by a block of steel. These edges of the aluminum tube are clamped, and therefore the block runs into the other end. It crushes the tube. Now the dimensions are given here, and there is a 2 millimeter gap between these two, uh, as is done by this YouTuber, and the block has initial velocity of 25,000 millimeter per second. The units that I'm using here are exactly what this person is using, and there are tons, millimeter, megapascal, and newtons. Okay, this is a very common unit that's being used. Now, uh, as far as the mesh goes, the block is modeled with three-dimensional continuum linear elements with reduced integration with a global size of roughly 10 millimeter, and the aluminum tube is made of shell elements with reduced integration, four-nodal shell element with reduced integration with that size. The steel is assumed to be elastic, uh, and the information is given here. The aluminum is elastic plastic with uh, isotropic hardening rule, and the information that you need is given here. You need the yield strength, and then the stress at a particular plastic strain. So these two points make it a linear variation. We're assuming it's linear variation. Now, as far as the contact goes, it's a general contact between the two pieces, so everything is done automatically by the software. You don't have to decide on the master and slave surfaces or primary and secondary targets, and the program will do it for you. And it's assumed that the friction coefficient between the parts, all surfaces, is zero point 0.3. The total duration, everything else is default. The total duration of the impact is simulation is 0.02 second or 20 milliseconds. Okay, so let's go ahead and make these. So I'm going to go to 3D Experience. It's an assembly problem. So let me insert, right-click, insert a 3D shape. That first one is going to be my steel block. So let me rename this thing, properties. I'll call it steel block. Uh, September of 2023. Actually, let me call it tutorial one. tutorial 1. Okay, and let me copy this thing because I need the same thing under instance. This is so that I can find things later on if I wanted to quickly, right there. And let's make it. So I'm going to double click on this, double click on that. Oops, where are we? On the vertical plane, I will sketch. I'll sketch a centered, for simplicity, centered rectangle, and I'm going to dimension it. So this is 120 millimeter, 120 millimeter, and so is this one. This is also 120 millimeter. Okay, exit, and we're going to pad it by 120 millimeters. Now notice that I'm in generative shape design, so I can't pad, so I'm going to switch to part design here because I want to get a three-dimensional object. All right, right there. And then here is a pad in the other direction by 100, oops, sorry, in the other direction by 120 millimeters. 120 millimeters. So it becomes a square block. Later on, I'm going to put material on these. As a matter of fact, I can do that right now, no problem. So let's go ahead and apply. Go to the tools, and we're going to add a material. Create a material. Why don't I give this thing a name? So I'll call it uh, steel block. Steel block. Tutorial 1. Okay. Say all right. It's going to create it here. We have two choices. I can input my data right now in the thing that I created, or I can apply it and then input it. So it's entirely up to you. But let me see now. Let me look at these things by chronological order. I don't particularly like the way this thing works, but anyway, right there. Steel block tutorial 1, and we can input the material now, or we can apply and do it in the other window. It's entirely up to you. So I'm going to say apply, okay, and then I can close that, apply to this part, check mark. Now notice that here I can go and apply it, basically put the information here. I'm going to double click on this. Okay, it's structural, general options, density, and the density was for steel. It is 7.8 e to the minus 9 10 per millimeter tons per millimeter cube. Okay, and we go to the elasticity piece, abacus multiphysics, mechanical, elastic, and this one for steel was 210,000 MPa, or basically 210 GPa. Poisson ratio is 0.3, and that's all we need for steel, okay, because steel is going to remain elastic, and that's fine. So now we're going to go all the way to the assembly once again. Okay, we are in assembly design, and I'm going to insert another piece. Now notice that you can do it like that, insert 3D part, or you can also do it from here under assembly, maybe on the product modification. You can say insert 3D part. It's entirely up to you. So I'm going to do it like this: right click, insert 3D part, and again I'm going to change this. Right click, properties, and I'm going to change that to aluminum tube tutorial 1. Let me copy this thing because I have to, on the reference, give it the same name. I don't have to, but it makes sense. You say okay. So there we are, and we go make it. So double click on the shape shape. On that same plane, what was that, XZ plane, I will sketch essentials or sketch a square which is 100 millimeter by 100 millimeters. That's the size of the cross section of that tube. So let's do that. Over here it's 100 millimeters. Over here it's 100 millimeters. Okay, and exit. Now I want to create a surface here, but because we're in part design, we can't do that. We're going to have to go to generative shape design and look under extrude. So there is extrude. Oh, not this one. Under surface, on the surface, not wireframe, surface. There is extrude, and I'm going to extrude it, but I don't want it to start right there. I want it to start 2 millimeter away from that plane. So one way of doing that is to say, okay, start from -2 millimeters and go all the way to 302 millimeters. Okay, preview, but wrong, this is the wrong direction, so go in the other direction. Say okay. Now if you zoom in closely, you see that there's a 2 millimeter gap between these two. Anyway, you have to do this thing any way you want. You can do it by creating the parts and then moving them around, basically using move manipulate in the 3D experience, CATIA's 3D experience, to move these things around so that there's 2 millimeter gap between them. Okay, how about material now? So we're going to go to tools once again, uh, add a material, create a material. I'll call this thing aluminum tube. Aluminum tube, tutorial 1. You say okay. Okay, notice that it did created, should have created somewhere there with aluminum tube tutorial 1. We can say right click, apply. And I can close that, apply to this piece with a check mark. And now we're going to go and input our data. So double click on that. Okay, under structure, general density for aluminum based on the table that we had in the slide is 2.5 e to the -9. Okay, good. And then we go to abacus multiphysics, mechanical elasticity, elastic. For steel, for aluminum, it's 70,000. Wait a minute. Young's modulus. Let's check that. It's 70,000 MPa. 70,000 MPa. Poisson ratio 0.3. Okay, good. And all right. Now we're going to go to plasticity. Metal plasticity. Plastic. Oops, not here. Click on plastic. It's isotropic hardening, so bilinear, so yield stress is 250 megapascal. I have set the units so that they are in megapascal because you can set your units in preferences, you know that. Zero plastic strain, that means the yield strength, and then 300 megapascal at the plastic strain of 0.1. What I'm doing is basically this data. And then we say, okay, good. There's nothing else to do. So we are done here. Let me go all the way to the top, and save everything. Okay, so for meshing purposes, first we're going to mesh. Now notice that the scenarios here called structural scenario creation. This is for, if you don't want to do explicit, don't use this. Sorry, if if you want to use Explicit, don't use this because Explicit license is not here. You have to go to mechanical scenario creation. I also want to remind you that those of you who have seen some of the videos on axisymmetric analysis, you have to go there. You cannot do axisymmetric analysis over here. But in the case of Explicit, also you have to be here. Now, as far as the meshing goes, the meshing is identical. This is where you do the meshing. Doesn't matter what you want to use. So let's do the meshing first. You create a structure, yeah, automated mesh, right? And it's an empty one because we're going to do the meshing ourselves. Empty. Good. So we're going to include these three parts. Oops. You say OK. Now, let's do the mesh for this shell first, another the aluminum tube. So we're going to go to mesh, and there is your surface mesh, triangle mesh. That's not what we want. We want this one, surface quad mesh. You click on it, you select that piece, and it's linear right here. And 5 millimeter is the thickness, or not the thickness. 5 millimeter is the size of the uh, shell mesh right there. See that 5 millimeter? All right. And that's pretty much it. You mesh it. There we are. Okay. Now we have to do something later on. You'll see there's something we need to do later on uh, that I'm going to do that. Okay. Now, then we're going to do a sweep mesh here. The problem is that in order to do a sweep mesh, you have to mesh this top face with a shell element and then sweep it down. Okay, so here's what I'm going to do. I'm going to click on the same thing here, surface mesh, surface quad mesh, on that surface. Now, I don't want this whole thing to be meshed because if I mesh it now, the entire box is going to be meshed. Click on this eraser here. It says, okay, what do you want to keep? I want to keep only this top face. And then we say, okay. And the size is going to be based on the slide here is 10 millimeter, okay? So 10 millimeter. All right. And then mesh it. There we are. And then we say, okay. Now we're going to do a sweep of this through that thickness. So we go to we are in meshing. We go here. It says extruded sweep 3D mesh. You click on it. It says, okay, what do you want me to basically sweep? The support is oh yeah, the body right here. The support is that three-dimensional object. Just select this box. Okay, and then how many layers do you want? We want 12 layers. 12 layers right there. 12 layers. We counted 12 layers this way, okay? And the size is roughly 10. You say mesh, there. Now, this guy, the second guy, we don't need. You have two options. You can either delete it or deactivate it. This is not going to be participating in our calculation. So you have two choices. Right click, deactivate, or simply delete. I'll delete it. The only advantage of keeping it is that if you ever have to change the size of this block, then because you deleted it, you have no choice. You're stuck, kind of stuck. Okay, good. Now we have to do the properties. So you click on the properties here. Let's do the solid one, the solid section. You click on it. Now we have to take this three-dimensional object. You select it, part body. Notice that the material is selected correctly, steel, and you say OK. And then you do the shells section. You select this whole thing, basically the entire tube, the extrude, and the aluminum is selected, and the thickness, don't forget the thickness here is 1.5 millimeter. Shell thickness is 1.5 millimeter. Notice that these are created here. You have the surface mesh, shell mesh, solid section, and shell section. Let's update it so that these update marks go away. Good. And we save it. Excellent. So we are done with meshing. The only problem is that the elements here, these elements are S4 four-noded shell element, but they're not reduced. We have to change that later on, and we will. Okay. There are different ways of doing it. I'll show you one way, one way to do it, and we'll do that later. Okay. So let's go ahead to uh, our compass up here and go to the mechanical scenario creation, not the structural scenario creation, because this does not have explicit in it, but over there. This is one of your applications here. I'll put it in my favorite ones, but it's right there. You click on it. Okay. Now, finite element model, you select it, right click. This is the one that we just created. See, it's right there. See, select it. We say okay. Oh, I really didn't want to do general. I wanted to do structural, but I forgot. Okay, so that's no problem. Uh, You know what? I'm going to delete this, do it again. Oh, I guess it won't let me delete it. That's okay. Uh, general will also work, but since my problem does not involve any heat transfer or things like that, I should have just said structural. It doesn't matter. Okay, good. Now, all right. So let's go ahead here and first of all, I don't want to see my mesh here. So let me right click and do what is that, visibility manager. Okay, and say I don't want to see my model. Okay, well actually I don't want to see my model. I want to see my model. I don't want to see my mesh right there. Okay, good. It's easier to do some stuff here. Okay, good. Now we're going to go to maybe we should do a procedures first. Click on the procedures. We don't want to do implicit. We want to do explicit, right there. See, procedures, explicit, and the total duration is 0.02 seconds, 0.02 second, right there. Okay, and that's obviously this nonlinear geometry must be included, so it's already by default included. Better be included. Okay, all right. Now notice that I can double click. When I did this immediately, it created this line for you, element type assignment. Double click on global element type assignment. Double click on this and notice that your brick element is already reduced type, but the shell element is not reduced. So you change this thing to reduced. Okay, S4R, S4R, and we say okay. So as soon as you created that explicit step, it gave you these additional things. Okay, good. Now let's go ahead and apply our boundary conditions. You click on it and you clamp. You clamp what edges? This edge and that edge and that edge and that edge. These four edges are clamped. Four edges are clamped. You say okay. All right. Now we have initial velocity, initial conditions is initial velocity right there. Now notice that you have some stuff here that if you had said general, structural, they may look different, okay? But we only, because I said general analysis case, then you get some additional stuff, it doesn't matter. So here we are, initial velocity of this piece. Okay, so let's try. What you want to do is not a face, but the entire block. Okay, and there are different ways of doing it. For example, you can block. You can just make a box around it. Oops, wait a minute. Let's see if we can. Let's see if this is the easiest way of doing it. Move this thing aside. Can I do this? Yeah. So one pad is selected in the X direction, and the value is 25,000 millimeters per second or 25 meters per second. Since I didn't change the unit for velocity, I can type either 25,000 mm underscore s or just put 25 here. And then we say, okay. Okay, right here, initial velocity. What else do we have? That's pretty much it. So now we have to specify the contact conditions. Okay, the contact conditions is under interaction. First, you create that friction model. So let's do the contact. See that contact property under contact interactions tab. You have contact property. You click on it, and you select the friction. You create one, specify friction option. Okay, it's Coulomb. That's fine, and the value of it is 0.3. The friction coefficient is 0.3. Everything else is going to be default. Okay, so yeah, can I close that? Should be able to close it. Yeah, okay, good. So I did create a friction model. It's right here, somewhere there. Wait a minute. Oh, here, interaction, uh, contact property one, which I was going to call it friction, but that's okay. Contact property model, just leave it the way it is, no problem. Good. And then we're going to do general contact, right here, general contact. Remember, this is what we're going to do. General contact, friction coefficient, everything else is default. So be careful here, make sure you change this thing. You change this thing from default, which is frictionless, to contact property 1, where we apply the 0.3 friction coefficient. Nothing else you have to do. All surfaces, these are all going to be automatic. Everything is going to be included. We say OK. All right. So notice that we have a friction model here with the value 0.3 and general contact. We did it right there. And that's pretty much it. There's nothing else we need to do. So what we're going to do is, let me close that for a second. First of all, we save this, assuming that I didn't forget anything, and I don't think I have, we'll see. Okay, so we're going to go to simulate. Let's do a model and scenario check. You click on this. If there are any major thing, it's going to pop up. Model checked. Okay, no problem. Let's do this one. This is simulation check. Say okay. This is going to be fairly quick. Okay, it's doing it. It's done. See that? And then we're going to run it. Now, I have a relatively cheap laptop, okay? And I think there's only one processor, maybe two cores. I'm not sure. I mean, it says, I think I have only two cores. I'm not 100% sure. But anyway, there's nothing multi-processor or anything like that. What I want to do is show you what is the wall clock here. So notice that it says 9:34 p.m. Let's go run it 9:34 p.m. and see when it actually physically finishes, because many of these problems, these video tutorial, they stop it because they don't want to record while this is running. But I started at 9:34 and we're going to watch and see when it's going to finish. It's not going to take more than probably 2-3 minutes at most. We have a record of the iterations here. There are no iterations here. Time steps is what we are dealing with in explicit dynamics. Okay, so notice that this is the actual total time. Remember, this is supposed to go to 0.2. This is the wall clock. In other words, it matches the number that you see down here when it finishes. So 22 seconds, for example, etc. So we'll see how far it's going to go. It's pretty quick. But this is a very simple model. I'm not doing a car crash, into a wall. That is going to take a lot longer. You may need to run the software on a complicated, or a expensive laptop or a supercomputer for some time. This is a very simple problem. Let's go. So right now the total time is 0.006. This is supposed to go to 0.02, okay? And this is the actual physical number of seconds wall clock, okay? Notice it's almost 1 minute gone, and this says 9:35. We're almost halfway through. And this is the number of increments. Remember, in explicit dynamics, you do integration, step-by-step integration. So at this point, you have 19,000 steps. Okay. This is 54% complete. You can see that halfway through. Remember, we are not assessing accuracy here. We are trying to see how the steps, how the interface changes when you go from Abacus CAE, that is the work of this fellow, to the 3D experience. I'm not claiming that my results are accurate because I'm just showing you the step. I'm not, we don't even know if these results are accurate because you really have to do some, some parametric study or mesh conversion study and things like that in order to have any assessment for the correctness of validity of the explicit dynamics. Explicit dynamics, basically, you get all the colors that you want. It's just that they may not match the reality for different reasons. Okay, so 94% complete, and this is going to go to 0.2. It's all done. Notice that it's exacting result. The wall clock says it's about 3 minutes, and this is almost 3 minutes. Okay, right? So 180 seconds. Good. So we close this. All right. Now let's animate. Well, I mean, obviously you can look at what happens when you crush it. You can see that. And then after a while, actually it stops and bounces back. Okay. But you can animate it too. So let's animate this. And you can make it control the speed. You click on this guy and go to a different speed and not as fast. Okay. If you look at the view from the side, you can actually see the rebounding of the block right there. So let's see. Just a second. This is where it rebounds. Okay, right here. It makes these things fold, the shell aluminum tube to fold, and then at some point it stops and bounces back. Now, there are a few things you can do. One of them, if you want to see the different kind of a view, let me select this, and you notice that what I did, I selected the contour, and I go here, and I say, okay, I want you to show me the cut view right there. Okay, say okay. There we are. This is the cut view of the channel. That's the one mesostress. You can look at the displacement, for example, right there. Obviously, this is all red because that's the most displacement. And note, let's say that we want to see the plot of different energy components of the problem. So you go to where are we here? This is in under display. Under plots, we go to plots right here, and here is the XY history data. What is that? Is this the one? Yeah, yeah, XY plot from history, and this is the, let's do the kinetic energy first. Kinetic energy, all kinetic energy. Say okay, there we are, and let's do another one on top of this. This is the kinetic energy as a function of time. And another one, notice that I did the uncheck this because I want the plus to appear on the same XY axis. So let's do the uh, artificial energy. There we are. So another one, strain energy, total strain energy. There is this, and then finally the total energy. Okay. So remember, in explicit dynamics, this artificial energy must be low, and it is, as you can see, it's this red stuff. It is, yes, this pink one. Okay. One more. Let's do the total energy, which is somewhere here. Total uh, total energy balance, which is that total energy is right up there. Okay, and that's good. So in the future, in some other tutorials, what I will do, I will change that block, which I meshed it with solid element into shell elements, uh, and then later on we do it with a rigid analytical surface. So this problem is going to be done three different ways. The indenter is a solid object, the indenter is a plate, and finally the indenter is an analytical rigid surface. Okay, and that takes care of the first tutorial. Good luck.